Hello everyone and welcome to the Ask the Expert series with Altair. And today we'll be talking about Feko's asymptotic solvers in detail. The image right here shows all the different types of solvers that Feko offers. So EM simulation is based on numerical methods and Feko offers a number of such electromagnetic computational methods. User can select these methods based on their application as well as the computational resources that they have. So all of these different methods have different formulations, which means that they have different strengths as well as weaknesses. If we start by antenna and circuit level design, one will need rigorous and accurate methods such as MOM or FEM. While if we are targeting a wide frequency band application, we switch to temporal FDTD method. These methods are very well suited for small structures before 10 wavelengths and complex materials such as human body or even circuit layers. But once we move to electrically large antennas or antenna placement on large structures, we move to the multilevel fast multipole method using convergence algorithm to make simulations lighter in terms of computational aspects while keeping good accuracy. Now, if we continue to move up in terms of structural dimensions, we prefer using what is known as the asymptotic methods, such as physical or geometrical optics or uniform theory of diffraction. So these asymptotic methods are nothing but high-frequency approximation methods. These methods provide faster results with less computational resources. Feko also provides true hybridization between these two types of solvers, which is the full wave solvers and the asymptotic solvers. So what happens when you have to solve a complex antenna on a very large structure? So what you can do is assign a full wave method to the antenna while assigning an asymptotic method to the large structure. By hybridizing these methods, we can couple two methods together to achieve an optimum solution. In order to solve these complex problems using these computational methods, the structures need to be meshed in a certain way. So each computational method has its own way of meshing. For example, methods such as MOM or MLFMM, physical optics, as well as rail launching geometrical optics, they all mesh the surface with triangular surface meshing. While the large element physical optics meshes the structures with large triangular surface meshing. We also have the finite element method that uses tetrahedral volume meshing, as well as the finite domain time difference method that uses voxel meshing. The UTD, which is uniform theory of diffraction, uses geometry-based meshing or phase-based meshing. Lastly, a few of the methods like MOM, MLFMM, and RLGO also offer large curvilinear meshing with higher order basis function. So all of these different methods are based on different formulations as well as different meshing aspects. So as I said earlier, all of these methods have their own strengths and weaknesses. For example, we have the physical optics method, which provides full hybridization with method of moments and MLFMM and is well suited for antenna placement. We also have the ray launching geometrical optics method, which is again well suited for antenna placements, antenna integration with radomes as well as lenses. It takes multiple interactions into consideration. We also have the large element physical optics, which provides full hybridization with method of moments as well as MLFMM and is well suited for antenna placement scenarios and provides fast results. Lastly, we have the faceted UTD or the uniform theory of diffraction method, which is well suited for large propagation scenarios where multiple interactions have to be taken into consideration. Having said that, each of these different methods have their own cons or disadvantages which have to be considered before you choose them for any application. So here we have a comparison table of an antenna placement problem on a large structure. The same problem has been solved with different computational methods at different frequencies, and so you can see the comparison in the table here between the memory requirements as well as the time that was required to solve them. So here for around 40 megahertz, you can see that there's a comparison between the traditional MOM method and the adaptive cross approximation method. The same problem at 40 megahertz, which was not solved with MOM, took only about 1.3 hours to be solved with ACA. Similarly, at around 200 megahertz, which is about 80 lambda of wavelength, the problem was solved with both MLFMM as well as a hybrid solution of conventional MOM and PO. So while MLFMM took about 6.8 hours and 45 gigabytes of memory, the hybrid MOM-PO solution provided the same solution with just 5 gigabytes of memory and 12 minutes of runtime. And as you keep on increasing the frequency to the gigahertz range, for example, between 1 to 5 gigahertz, there's a comparison between different hybridization methods. For example, the method of moments with large element physical optics. It takes only about 15 minutes and only 936 megabytes to solve the same problem, but in the gigahertz range. So having said that, asymptotic methods provide a really optimum solution where you have computational resource constraints.
Now that we've talked about different solvers in Feko, let's talk about how to set these solver settings. So the default solver in Feko is the method of moments solver, and the rest of the solvers can be specified per model, per phase, or per region. As you can see in the image here, all the high frequency solvers can be specified per phase, while the full wave solvers can be specified per model or per region based on the specific solver. You can find more information about these solvers by going to the documentation section. You can open the Feko user guide and go to the Feko solution methods section. As you can see here in the Feko solution methods, all of these methods have been described in detail. Also, to help the users in deciding which methods to go for based on their specific problems, we have a generalized list that can help you choose the solver based on your problem. For basic problems of antennas, the best suited methods have been highlighted here. So based on different types of antennas, the solvers that are best suited or well suited for those kind of applications have been highlighted here. Also for certain complex applications like FSS or periodic structures, microstrip circuits, etc., the best suited solvers have also been highlighted for these applications. I would now quickly like to jump into the demonstration section. So I'm going to demonstrate an antenna placement problem with two different types of solvers, one being MLFMM and the other being physical optics, just so that you can get a fair comparison between the two solvers and the memory requirements as well as the run times between the two. So I'm going to open CAD Feko and go to the component library. Component library has a number of different types of antennas as well as different types of structures as well. So I'm going to choose the plane option here. I am again going to go into the component library, and here I will be working with a low profile blade antenna. So I'm quickly going to search for a blade antenna. The frequency that we're going for is 1 gigahertz. I'm going to select the solver type as MLFMM, and the antenna is for a single frequency. So you have different types of options here to select like a range of frequency as well, but for the sake of this demonstration, we're going to go for a single frequency. As you can see here, we have the planes as well as the blade antenna. The blade antenna here is at its default location, which is at the 000 coordinates. So here I'm just changing the orientation of the antenna. So in order to place the antenna, you're going to select on the antenna geometry, right click, go to transform and select translate. So, so here you can go from the 000 coordinates to your destination coordinate or the desired location where you want to place the antenna. Once that is done, I am going to union this geometry. Once the geometry is unioned, the next step is to add a port. So we're going with an edge port here, and I'm selecting the positive and the negative faces. Once a port is specified on the antenna, the next step is to add a source. So in this case, we are adding a voltage source. So now your model is pretty much ready. You have your airplane structure, the antenna placed on it, the frequency has been defined, the port and the sources have been defined as well. So the next step is to request for the outputs that you'd like to see. In this case, we would request for far fields. So now we're going to mesh this model. We'll be using the point refinement option here. So what we're going to do is we're going to mesh the area around the antenna with a finer mesh so that the airplane structure can be meshed with a coarser mesh. In order to use the point refinement option over here, you have to specify the radius as well as the mesh size. So the radius will define the area around the antenna that has to be finely meshed. And then you have to specify the mesh size at which you'd like to mesh that area. So here we are using two different types of point refinement options with different radiuses as well as mesh sizes. Once the meshing rules have been set, we can go ahead and save this model. Now let's create a mesh for this model. I'm going to go with the coarse option. Once the model is meshed, it is ready to run. So you can go to the Solve and Run tab and click on the Feko solver, which starts the solving process. After the model finishes running, you can open the Post Feko from the Post Feko option here. So Post Feko is the post-processing tool in Feko, which is used to view the results. So in Post Feko, you can view the results that you requested for in the CAD Feko. You can choose from various different types of graph options. So here I have chosen to see my far field results in the polar plot form. So I am viewing these results in different planes, naming X, Y, Y, Z, and X, Z. Now let's go to the out file to check our processing times. As you see here, this model took about 14 hours to run with the MLFMM solver. So what we are going to do now is we are going to compare the same model but with an asymptotic solver, and then we'll compare the results between the two. As we discussed before, in order to change the solver, you have to go and select the model geometry. Once you click on the geometry, you can select the faces of the model. Select all the faces that we'd like to assign an asymptotic solver to. Right click on those, go to solution, and then select the solver. In this case, we are using the large element physical optics. So here the default solver is used for the antenna, but to solve the plane structure, we've selected to go with LEPO. Now we can go ahead and save this model with a different name. Let's mesh the model. We're going to keep the mesh size as coarse. We can clearly see here that the mesh is way more coarser compared to the MLFMM mesh. Let's save this model and run it. PostFeco allows you to add different models to compare the results. So here we are going to compare both the MLFMM results with the LEPO results. So I'm going to open each of these polar plots and plot the LEPO results along the same cut planes. This graph clearly shows that both of the results from MLFMM as well as large element physical optics, they both look very much in agreement with each other. Now let's go to the out file and compare the run times. So here we can see the run times from MLFMM model, which was about 14 hours. Let's open the out file from the LEPO solver. And you can see the difference in time. It hardly took a few minutes for this model to run, and yet the results from both of these solvers show good agreement with each other. Now, in the last model, we ran the model only with large element physical optics, and we decoupled any solutions from method of moments. So just for the sake of comparison, let's try to turn on this option for the coupling between MOM and LEPO. We'll now save this model with a different name. Go to the Solve Run tab and then run it with Feko Solver. Again, let's add this PostFeco file to our previous PostFeco model that's already open here. So now we have three different models added to the PostFeco session. One which was run with MLFMM, the other one that was run with just LEPO without any coupling, and the third one that has coupling between MOM and LEPO. So as we plot the results with the coupling, you can see that there is a better agreement when it comes to a comparison with the MLFMM results. Let's have a look at the runtimes as well. So I'm opening the out file right now. And you can see that the runtime is only 0.3 hours. So this did take a little bit more time than the decoupled MOM and LEPO solver, but it is still faster than running the traditional MOM or the MLFMM method. So with that, I'd like to conclude this session. We've gone through different types of solvers in FICO with a focus on asymptotic solvers, and we've discussed about a few advantages that the asymptotic solvers in FICO present, the applications where different types of solvers can be applied.